Hey, Math 30-2. Today we're going to look at some Pauli and sine functions, lesson 3, modeling data using polynomial functions. So, analyzing data. In exponents and logs, lesson 5, we analyze sets of data relating to quantities such as population and time, age and percentage decay, etc., etc. We determined the equation of the exponential function or logarithmic function that best approximated the relationship between the two quantities using the statistical technique called regression. So we're going to carry that out in a similar analysis today, but we're not sure if the quantities can be expressed as a linear, quadratic, cubic, or any other type of regression. As before, plotting the data on a grid and observing the pattern of points will enable us to choose the most appropriate type of model for the data. So let's consider this data below. The concentration in milligrams per liter of a medication in a patient's blood is measured as time passes. Susan has collected the following data and is attempting to express the concentration as a polynomial function of time. A. Let's plot the data on the grid to investigate the type of relationship between the concentration and the time. So, let's go time 0. We'll put the time down here. And concentration over here. All right, so time 0, concentration 0, that's going to go right there. Time of 1.5 hours, concentration will be 26.9. So we haven't really got a grid here, so let's make a grid. 1, we have to get to 9. 2, 3, 4, 5, 6, 7, 8, 9. All right, time in hours and concentration in milligrams per liter. We have to get all the way up to almost 50. So let's say 10, 20, 30, 40, 50. All right, so now let's plot these 0 and 0. 1.5 hours and 26, 10, 26 might be right about there. 3 hours and 41. 4.5 hours and 47.8. 6 hours and 46. 7.5 hours, we're down to 36.8. That's maybe about here. Oop. 6, 7.5. I guess that should be over a little bit. 7.5 would be 36, right about there. And then 9 hours, we're at 20.3. So there, we've plotted the data. All right. Select the best alternative for the type of relationship exhibited by this data. So if you recall, constant means it's going to be horizontal or vertical. Linear would be some kind of an oblique line. Quadratic would give us a parabola opening down or maybe up. And cubic would give us something that bends and turns like that. All right. So this looks like it's only got one bend in it, and it's opening down. So this might best be described as a quadratic function right now. So the rest of this page, regression. Remember, exponential logarithmic functions, lesson 5, we learned 4 features of the graphing calculator. A summary of these is given below. So the rest of this page and all of the next page, page 350, gives us all the information to remember how to use regression. All right. Well, you can read through that or follow along. I'm just going to show you how to do it, and we'll base it on the information from example 1. So the concentration in milligrams per liter of a medication is given. We've got that already. We already plotted it on the last grid. Now it says on a graphing calculator, enter the data into 2 lists. We should not do that. Put time in list 1, concentration in list 2. Create a scatter plot. We will do that. We figured it best matched a quad function, so let's use quadratic regression to get an equation of the polynomial that best fits this data. All right, so we're going to do all the stuff on our calculator. So get your calculators out and let's try this. So on our graphing calculator, they want us to enter the stuff in lists. So hit your stat button and press enter for edit the lists. If you want to clear your lists, make sure you go up to the list, make sure it's highlighted and press clear enter. So we're going to clear lists 1 and 2. And we're going to enter the time in list 1. So 0, 1.5, 4.5, 6, 7.5, and 9 hours. And in list 2, we are going to put the concentration. So that's 0. All right. 26.9, 40, 41.2, 47.8, and so on. So we now have our data entered in our lists. Create a scatter plot. So you go to your y equals screen. And to get your scatter plot highlighted, we want to do plot 1. So you actually go second function, y equals, into your stat plot. Right now your first plot should be turned off. You want to press enter. And see how plot 1 is off, because off's highlighted. You press enter to make plot 1 on. Make sure your on button's highlighted. Go down. That's our scatter plot. Make sure in list 1 we have in the X list we have list 1, in the Y list we have list 2. And here, what kind of mark do we want on our graph? Either a box or a plus sign or a dot. That's fine. Next step, we want to make sure we get a window setting that matches our data. So our X list is time. Time goes from 0 to 9 hours. So maybe so we can see the axis, maybe we'll just go from -2 to 10 hours is fine by a scale of 1. And our concentration in milligrams per liter is on our y-axis, and that goes from 0 to about 50. So maybe we'll go from -10 to 50. We'll go by scale of 10. So if we press graph now it looks very similar to what we had in our notes when we plotted that data. All right, so we have on our graphing calculator, we have put the data in 2 lists and we have created a scatter plot. Now let's create a quadratic regression equation. All right, so on our calculators, we'll now go to our home screen, second quit. So you can clear your home screen. And we will go stat button over to calculate. And we're going to go down until we see number 5, quadratic regression. You could have hit number 5 and that would have got us there. Now I'm going to tell the calculator what lists to use. So second list 1, comma, second list 2, comma. And we also want to save it into our y equals screen. So hit your variables button, go over to y variables. We're dealing with a function, so press enter. And we wanted to go into y1. So what we've told the calculator is to do a quadratic regression for lists 1 and 2 data and store that equation into y1. You press enter and there's our quadratic regression equation. All right. So based on that information, it wants us to write the parameters in our notes to 2 decimals. So you guys have that in your calculator. We should have it written in our notes then. So it looks like this. To 2 decimals, we would say C equals A was the parameter -1.86 t squared, plus B parameter was 18.76 t, and our C parameter was 1.21. All right. So if you look in your calculator, that should match up. -1.86 is A. B is 18.76, and C is 1.21. All right. Now, part B, on the calculator, display the graph of the regression equation over the scatter plot and use the graph to answer the following questions. All right, we can do that. So go to our graphing calculator. If we go to our y equals screen by hitting graph, because we stored that in y1, our regression equation, the curve will show up on our graphing calculator, and it looks like it goes through most of those points that we gave it. So it almost goes to the middle of all those boxes, but it touches all those boxes. So let's answer the question from the book. There are domain restrictions on the quadratic function determined from the data. The minimum value for time is 0, and the maximum value for time is the intercept on the graph. That intercept on the graph is right here, so maybe we have to increase our x a little further. Determine the domain for this model. So for our model, we maybe better change the window because we can't quite see that x-intercept. So let's make our window for x go to a maximum of maybe 12, and I think we'll be fine. So now if we graph it, there's our scatter plot, there's our quad regression equation, and we're looking for a domain restriction. We know the minimum time is 0. Now we're looking for the maximum time. So let's figure that out. That x-intercept is called a 0. So go to your y equals screen, and we want to turn the scatter plot off for right now. So just press enter. What that will do will tell us just our equation will be showing in the graphing calculator window. So no longer the scatter plot. And now I can find that x-intercept without worrying about being in the wrong mode, dealing with the scatter plot instead of my equation. So to find that x-intercept, we're going to go second calculate. And we're looking for a 0, number 2. So you press enter. So the 0 of the function that we want to find is the second blue circle over here. We're looking for this x-intercept. So it's giving us a direction, get left of that x-intercept. So left of that might be at the point 9.5. You can see the cursor show up at 9.5. That's left of that x-intercept. And now we could use our arrow keys if we want to get right of it. So I'm definitely right of that now. So I can press enter. You see another arrow show up on our screen. What it's saying is it will now find the x-intercept between those 2 points. Do I want to make a guess? No, I don't have to make a guess because I've made good boundaries. Just press enter, and you can see that the intercept shows up right in that blue circle. All right, so we found our x-intercept. It is at 10.159521. So we'll just say it's about 10.16 would be fine. So if I want to state the domain of this function could be written as the x-coordinate, and our equation is t. So t such that the minimum value is 0. So t is greater than or equal to 0, but less than or equal to 10.16. And t's any real number. All right. The doctors decided that the patient needs a second dose of medicine when the concentration in the blood is less than 10 milligrams per liter. If the first dose of medication was given at 9 a.m., at what time should the second dose be given? All right, so if we need to the concentration is less than 10, at what time does that occur? So concentration is 10, that goes in for C. Negative 1.86 t squared plus 18.16 t plus 1.21. So there's the equation we have to solve. All right, so we could solve that equation for t. Well, it tells us to use the graphing calculator. So if I want to use the graphing calculator, I'm going to let y2 equal 10. And we already have y1 equaling this part of the equation in our graphing calculator. So I can now find the point of intersection on my graphing calculator. So let's go do that. All right. So on our graphing calculator, you go to your y equals screen. In y2, we're going to say y2 should equal 10 milligrams per liter. Graph it. There's our line, 10 milligrams per liter. When the dosage is less than 10, you should get another shot. So we're looking for this point of intersection right there. All right, so let's go second calculate. Number 5, the point of intersection. First curve, yep, it's on the y1 curve. Second curve, it's on the line y2 is 10. Do you want to make a guess? Yeah, let's get closer to this point of intersection because there's more than one point of intersection. All right, we want the one when it gets less than 10 over there. And that point's at about 9.6 hours. All right, so back in our notes, we should say t equals 9.6 hours roughly. All right. So this was given at 9 a.m. I'm going to go 9.6 hours after 9 a.m. So 9.6 hours, go back to our calculator. So it's 9.6030042. All right, so 0.603 and so on times 60 minutes will tell us about 36 minutes. So it's going to be 9 hours, 36 minutes after 9 a.m. So what time is that? So next shot, the second dose should occur at 9 a.m. plus 9 hours is 6 p.m. So 6:36 p.m. All right. Great. Let's have a look at example 2. A research student was investigating the relation between job satisfaction J as measured by an employee on a scale from 1 to 10. That's our x-axis, and productivity P as a measure of the employer, measured by the employer on a scale of 1 to 100. So they give us this chart down the left, 12 employees. Data from 12 employees is given in the chart, and a scatter plot from that is drawn. All right. So A, the student looked at the scatter plot rising from left to right and suggested that productivity could be expressed as a linear function of job satisfaction. All right, linear function. Perform a linear regression on the data and determine a relationship in the form P equals A times J plus B, giving A and B to 2 decimal places. So what do we have to do? We have to put the job satisfaction into list 1 and the productivity in the list 2. So make this list 1, make this list 2, and perform a linear regression on this stuff. All right, so let's do that. Go to your calculator, go to your stat menu, hit edit, and let's clear these lists. Clear list 1 and list 2, and type in that data. Away you go, type that in, I'll do the same. All right, so I've got the data into my calculator. If you haven't, pause this until you get it into your calculator and then restart it. So once we have it in our calculator, we're going to perform a linear regression. So go stat, calculate, and we're going to do a linear regression number 4. All right, so you press enter. And again, we want it for list 1, comma, list 2. And let's store it in Y1 just in case we have to match the data. So variables, order Y variables, function Y1. Beautiful. Press enter. And there are parameters A and B. So let's write this in our notes. A is 7.91 and B is 19.89. All right. It's the equation we want. P would equal A, we said, was 7.91 J, plus B, we said, was 19.89. All right. Another student looked at the data and suggested that the relationship could be represented by a cubic function, which has a point of inflection. Perform a cubic regression on the data and determine a relationship in the form given where A, B, C, and D are 2 decimal places. All right, so let's go back to our calculator, perform a cubic regression on the same data. So stat, calculate, go down to number 6. That says cubic regression. You just hit the number 6. Again, list 1, comma, list 2, comma, let's put it variables, y variables, a function. Let's put this one in y2. Press enter. And we've got this equation given. A is about 3.2, B is negative 6.37, C is 45.90, and D is negative 44.21. So let's write that out in our notes. All right. So P would equal, A we said was 0.32 J cubed, B was negative 6.37 J, C was 45.9, and D was negative 44.21. Which model do you think best represents the data? Well, in order to figure that out, let's go back to our calculators and let's have a look at the data. So our window setting to match this data, job satisfaction was ranked from 0 to 10, so X go from 0 to 10. And productivity was ranked from 0 to 100, so Y score from 0 to 100. And what else do we want? We want to put our scatter plot on there. So let's go second stat plot and turn our scatter plot on. All right, so once the scatter plot's on, we know it's a scatter plot. We've got the X list is list 1, the Y list is list 2, and our marks. So if we graph it, there's our scatter plot, there's our linear regression, and there's our cubic regression with a point of inflection. So looking at those two, which graph goes through more boxes? Well, I would have to say the cubic regression looks to go through more boxes. If I just turn off the linear one and press graph, it's 1, 2, 3, 4, 5, 6. It looks like it hits about 4 or 5 right in the middle and touches most of the other ones. If I go back to the linear regression, turn that one on, and the cubic regression off, and press graph. Well, the linear regression hits a couple of them, but there's many points above and below the line. So for my bet, I would say the model that best matches this is the cubic model. All right, so you guys can do questions that you're assigned. Where you go.